Well, hello, welcome again to Math 315 on Analysis and Topology, and this is the third recording for Chapter 8. So we've been looking at power series, and you should know at this stage how to find the open interval of convergence of a power series. And we finished off by looking at how to add and multiply, which was slightly more complicated, to manipulate these power series. Well, in fact, we can do even more than that. We can differentiate and we can integrate power series as long as we stay inside the interval of convergence and nothing goes wrong. Now, as I mentioned before, power series are lovely. They're very robust. You can kick them around and do all sorts of lovely things with them. Nothing goes wrong as long as you stay inside the interval of convergence. There are other sorts of infinite series, not power series, where this doesn't work anymore, where you can have a perfectly good convergent series and you can differentiate it and it'll blow up in your face. You'll suddenly diverge on you and go off to infinity. It doesn't happen for power series. So suppose then we have a power series which converges on some open interval AB. Then we can differentiate the series term by term, and the resulting series also converges as long as we stay inside the interval of convergence. Also, we can integrate the series term by term, and the resulting series also converges in that interval. Note that sometimes we can push the boundaries a little bit, and we can sometimes even include the two endpoints. And interesting things can happen when you do that. I'm not going to go through the proofs of these here. They're rather fiddly, but you can find those in various books. So I'm just going to state these facts without proof here. I want to do a very long example, a rather extended example, but one I think is one of my favourites. It's a very interesting example where you can get some rather amazing formulae almost from nothing. Just starting off with the basic power series that we started with, this geometric series, and from this we're going to get lots of very interesting facts come out of this. So this is a fairly long example. You might need an extra page to write all the details up. So here's our basic power series, x to the k. So sigma x to the k, so again this is 1 plus x squared forever, and we've seen before this converges to 1 over 1 minus x as long as we stay inside the interval of convergence minus 1, x going from minus 1 to 1. So I'm going to play with this. Well, I've already done ones like this before. I'm going to replace x with minus x. We did that once before. So that becomes minus x. When you square minus x, you get just ordinary x squared. If you cube it, you get minus x cubed, and so on. And if I replace x with minus x here, I get 1 on 1 plus x. Now again, no damage done here. If my x is between minus 1 and 1, and I replace x with minus x, then minus x is also between minus 1 and 1. So this is going to still work as long as I stay in this interval. And I'll call this series star. Well, let's just play with this a bit. I'm going to differentiate both sides term by term. So I differentiate 1, I get 0. Differentiate minus x, I get minus 1. Differentiate x squared, you get 2x. Minus x cubed goes to minus 3x squared, and so on. You can see the nice pattern here. I'm going to get 1, 2, 3, 4, and so on. And if I differentiate this, remember I can write this as 1 plus x to the minus 1. Right, I can write this as 1 plus x to the power minus 1. And when I differentiate it, you bring the power down the front. You get minus 1. Decrease it by 1, becomes 1 plus x to the minus 2. And I can write down back in using that notation. So again, provided I stay x between minus 1 and 1, this infinite series, which is no longer a geometric series by the way, this infinite series converges to this quantity. And you might like to do a similar thing with this one. You can differentiate both sides of this, and I'll get 1 plus x plus, so I get 1 plus 2x plus 3x squared plus 4x cubed and so on. And you can differentiate this thing, and you should end up with, in fact, plus 1 over 1 plus x squared. So that's something for you to practice with and play. You can get an infinite series without all the negatives. So that's differentiating this series. So from basic series, we can get a non-standard series, a non-geometric series, in fact several of them. We can also take this line here and integrate term by term, and now things get a little bit more exciting. If I integrate both sides of this, you integrate 1, you get x. You integrate minus x, you get minus x squared on 2. Integrate x squared, you get x cubed on 3, and then minus x to the 4th on 4, plus dot 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 forever. Don't forget these are infinite series, so there's lots of other terms going on here. Now, here's the exciting bit. If I integrate 1 on 1 plus x, then I get log of 1 plus x. Now, when you integrate, of course, you pick up a plus c, so I've got to worry about this wretched plus c to see if we can work out what it is. Now this works provided my x, as I mentioned before, is between minus 1 and 1. So I'm going to pick an x value between minus 1 and 1. That makes everything nice and simple, and the obvious choice is to put x as 0 in. So if I choose x to be 0 into here, then I get 0, 0. All of these terms are all 0. I'm putting x to be 0, so I get log of 1 plus c. So I get 0 is the log of 1 plus c, but the log of 1 is 0. And so we'd simply get c as 0. So that c we picked up from integration turned out to be 0 anyway. And that gave us this remarkable formula here. X minus x squared on 2 plus x cubed on 3 minus x to the 4th on 4 plus forever. And again, you can see the pattern here. We're getting 2, 3, 4, 5, 6, and the signs are alternating. It's a lovely pattern here. And this infinite series, this power series, converges to the log of 1 plus x. Well, provided we're between minus 1 and 1. So, thinking a bit laterally here, you might think, well, I could use this series then, if I wanted to know, for example, what the log of 1.5 was, log of 1.5, I could put x as 0.5 into here, and take the first 20 terms, and that would give me an approximate value for the log of 1 plus a half. And that's true. A couple of things to say, however, is that this series does not converge very quickly. That is, you've got to take lots and lots and lots of terms before you get reasonable accuracy. The second thing is, well, this I can work out log of 1 plus a half, but I can't work out log of, say, 3 here, because I'd have to put x as 2, and 2 is outside of the range. And in fact, in the tutorials, we'll have a look at another way of getting a nice series for log, where you can work out log of numbers that are no longer inside this interval between minus 1 to 1. And in fact, that's what your calculator does. It's got it built in to, it's got a series for log, and which happens to converge reasonably quickly, and it takes the first 20 or so terms of that, and that's how it works out logs of things. Now I'm going to be very naughty here. I've said that our x must be between minus 1 and 1. So x equals 1 is not in the interval of convergence. However, I'm very tempted to put x equals 1 to see what happens. Now, I'm not proving to you here that you're allowed to put x equals 1. It turns out you are in this particular instance, but not by the theory we've been developing so far. But I'm going to not resist temptation here. I'm going to put x as 1 in, and look what happens. You get 1 minus a half plus a third minus a quarter plus a fifth, and so on. And you put x as 1 over here, you get log 2. And this is a very famous series. In fact, you may remember this is the alternating harmonic series that we looked at earlier. So it's not 1 plus a half plus a third plus a quarter. We know that diverges. But we looked at this earlier, that 1 minus, you change every second sign. We showed by Leibniz's test that this series in fact converges. And now we know what it converges to. If you believe what I've done, it converges to log 2, provided you take it in this order. I.e., if you sat down with your calculator or computer and you worked out 1 minus a half, and then you added a third, minus a quarter, plus a fifth, minus a sixth, and so on, the answer you get gets closer and closer to log 2, which is about 0.69 from memory. So that's a beautiful old infinite series. This goes back a long way in history. In fact, people discovered this fairly early in the piece in mathematics. Well, there's more. This is a lovely thing to play with, lovely series to play with. So I'm going to go back to our equation star again that I had here. And I'm going to replace x with x squared in this series. So replace x with x squared, that becomes minus x squared. Replace x with x squared all squared is x to the fourth by the index laws. X squared cubed is x to the sixth, and so on. And again, look at the patterns here. We're getting 2, 4, 6, 8, and the signs are alternating. And on the other side, I'm replacing the x here with x squared, so I get 1 over 1 plus x squared. Now again, if x is between minus 1 and 1, then x squared, well, in fact, is between 0 and 1, but it's certainly still between minus 1 and 1. So this is valid, provided my x is between minus 1 and 1, then all is well. So here's another infinite series. Now, you could differentiate this, but it gets a bit of a mess. But you integrate it, something really interesting happens. If you remember your inverse trig functions, when you integrate this left-hand side, you integrate 1, you get x. You integrate x squared, you get x cubed over 3. You integrate x to the fourth, you get x to the fifth on 5, then x to the seventh on 7. And again, look at the patterns here. We're getting 1, 3, 5, 7. Signs alternating. But the exciting thing is that when you integrate 1 on 1 plus x squared, you get inverse tan of x. You get the inverse trig function, plus of course a constant. Now again, I want to work out what this constant, so I pick something between minus 1 and 1. I put 0 in, and all of this is 0, and this is 0, so c is 0. And that gets me this beautiful series here, x minus x cubed on 3 plus x to the fifth on 5 minus x to the seventh on 7 is equal to inverse tan of x. Now again, I'm going to be naughty. We're not allowed to put x as 1 in. It's not in the open interval of convergence, but it turns out that it works. If you put 1 in, you do get a convergent series over here. So I'm gonna just close my eyes and put x as 1 in and see what happens. So you put 1 in here, you get 1 minus a third plus a fifth minus a seventh plus a ninth. Again, look at the beautiful patterns here. These are the odd numbers. And you put 1 into here, you get inverse tan 1. But, of course, now we get excited, I hope. Inverse tan of 1 is 45 degrees. That's pi on 4. And that gives me this remarkable infinite series expression for pi. So you can write pi as 4 times this infinite sum, 1 minus a third plus a fifth minus a seventh. And again, you have to add this up in the given order. It doesn't converge absolutely. But again, if you took your calculator and you took 1 minus a third, add on a fifth, minus a seventh, plus a ninth, and you kept going for several hundred terms, and you multiply the answer by 4, the number you get will be closer and closer to pi, 3.1415926. So we get this very famous series. This is, again, a very famous series that goes back several hundred years. A lovely expression for pi, an analytical expression for pi. Well, you can do more with these things, but that'll suffice for the moment. This is a very pretty example I hope you find. So one of the things we've seen so far is in looking at our power series that as we just saw, you can get power series that actually converge to some well-known function, like as we saw there, 1 on 1 minus x, or log of x, log of 1 minus x, or inverse tan of x. And in fact, it turns out we can do this more generally. So if f has derivatives of all orders, you may have seen this in earlier courses, has derivatives of all orders, that means you can differentiate it as often as you like in some open interval containing the real number a. Then we can form this series here. It looks very complicated, but I'll just go through it with you. So what you do is, you've got a point A, got some real number a, you evaluate f at a, you take the derivative of f evaluated at a times x minus a, you take the second derivative evaluated at a divided by 2 factorial times x minus a squared. The general term is you take the kth derivative of f evaluated at a on k factorial times x minus a to the k plus dot dot dot. And if I write that in sigma notation, it looks like this. Now this is called the Taylor series for f about x equals a, also known as the Taylor expansion of f about x equals a. Now you may have come across these in earlier courses in calculus perhaps. In the case when a equals 0, if we're expanding about the point 0, then the formula collapses down a little bit. It's not quite so scary. It's now f of 0 plus f dashed of 0x plus f double dashed of 0 on 2 factorial x squared, and so on. And it looks like that's it in sigma notation. And this is called the Maclaurin series for f of x. And it's named after Colin Maclaurin, who was Professor of Mathematics at Edinburgh about the bit after the time of Newton, but not much. In fact, I have one of my oldest books is a book written by this Colin Maclaurin. It goes all the way back to the early 1700s. It was called a treatise on algebra by Colin Maclaurin, very famous mathematician. So we're going to work out the Maclaurin series for e to the x. And this is rather nice. We're going to try, that is, what we're going to try and do is we're going to try and write e to the x as a power series, as an infinite polynomial. We're going to find a power series expansion for e to the x. And here are the calculations for it. So what we do is, there's our function, e to the x. Now, e to the x is a lovely function because when you differentiate it, it doesn't change. It stays exactly the same all the time. So if I put x as 0 in, e to the 0 is 1. If I differentiate e to the x, it's still e to the x. You put 0 in, you still get 1. You take the next derivative, you still get e to the x. You put 0 in, you still get 1. So all of the values of the derivatives at 0, they're all equal to 1. So plugging that into the Maclaurin series, we simply get f of 0, which is 1, plus f dashed of 0, which is 1 times x, plus f double dashed of 0, which is 1 times x squared on 2 factorial, plus x cubed on 3 factorial, and then you see the pattern coming out. And I can write that in sigma notation as sigma x to the n on n factorial. N goes from 0 to infinity. And we saw this one earlier. This is the power series we proved converges for all real x. Now this is very, very, very pretty because we're starting off with this function e to the x, the exponential function that we know and love, and we try and write it as an infinite polynomial, and look how simple it is. It really is remarkable that there's such a very simple pattern. We just get 1 plus x, we get x 2 factorial, 3 factorial, 4 factorial, and so on. That is lovely. That is very beautiful. The fact that you work out the infinite polynomial for e to the x and it's got a lovely pattern in it. This does not happen for all functions. There are some functions, for example, tan x. It has a power series, but you don't want to see it. It's pretty complicated. There are patterns there, but they're not very easy to spot. They're very complicated and very difficult patterns. But for e to the x, the the so-called Maclaurin series is very simple and it converges for all x. And now you see how your calculator works. The calculator has the first 20 or 30 terms of this series built in. It's got a little iterative process built in, and so when you ask your calculator what's e cubed, what it doesn't calculate, or e to the 1.7 or something. What it does is it simply plugs 1.7 into here and gets the first 20 terms or so, and because of the factorials in the denominator, this converges pretty quickly. So you can get really good accuracy just by taking the first 10, 15 terms of this infinite series, and that's how your calculator works out these things. Well, we can also do the same for some other functions, and we'll have a look at that in the fourth recording.